Welcome everyone. My name is Fan Gu from the National Center for Asphalt Technology, and I am the session chair of this session. This session is titled Geosynthetics in Pavements. A couple of things to know before we start the presentations. You will have the opportunity to ask questions during this session by clicking the questions button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are able. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any sessions that you attend. Please note that you will need to include the verification code showing this session to verify that you did attend this session and ensure that you receive the proper credits. Please enjoy the presentations.
Good morning, everyone. My name is Fan Gu. I am an assistant research professor at the National Center for Asphalt Technology. I'm going to present a paper co-authored with David Andrews from Propex Operating Company and Mark Marenfeld from Trademark Incorporation. Our presentation title is Evaluation of Bond Strength, Permeability, and Recyclability of Geosynthetic Products. Geosynthetic interlayers have been widely used in pavement rehabilitation. The major benefits of these products are stress relief and moisture barrier. As shown in the left figure, on the traffic loading, the geosynthetic can relieve tensile and shear stresses, thereby absorbing the fracture energy. In the long term, the geosynthetic interlayer can mitigate bottom-up fatigue cracking and reflective cracking distresses. The right figure shows the relationship between permeability of paving fabric and application rate of tackle. We can see the permeability of paving fabric reduces to 10 power minus 5 millimeter per second when the application rate reaches about 0.25 gallon per square yard. The moisture barrier function of geosynthetic can reduce the moisture damage to pavement and improve the bearing capacity of online layers. In this study, we would like to answer 3 questions. First is to quantify moisture barrier function of geosynthetic interlayer products. The second question is whether the use of geosynthetic interlayer products can provide adequate bond strength between existing asphalt pavement and asphalt overlay. The third question is will the milled geosynthetic fabric can adversely affect the engineering performance of new asphalt mixture containing recycled materials and milled pieces of paving fabric. We evaluated 6 different commercially available products, including polypropylene, and polyester combined, all fiberglass bonded polyester products. These products are coded here as PFR, PF, PMH, PMC1, PMC2, and PGM. We also provided the tensile strength and asphalt retention rate data in this table. To quantify moisture barrier function, we perform the falling head permeability test. We aim to simulate the actual field construction. As shown in the figures, we placed an old asphalt slab at the bottom, then placed an aluminum sheet, spring tackled, placed a geosynthetic on top, then compacted open graded friction coils on top of geosynthetic. After that, we removed the top slabs and cut the samples with 6-inch diameter. And then we used the wax to seal the site. After these procedures, we performed the permeability test using the Florida falling head permeability device as shown in the right corner, right bottom figure. Here are the permeability test results. The control is open gradient friction course without geosynthetic placed at the bottom. According to the Florida Department of Transportation specification, the asphalt layer can be considered permeable if the permeability is greater than 125 centimeter per second times 10 power negative 5. The open gradient friction course has a permeability greater than 20,000. It is a very high value. It is because the OGFC is designed as a permeable layer. We can see when we place the geosynthetics like the PFR, PF, PMC1, and PMC2, the specimen turned out to be impermeable. We conducted the two keys grouping analysis in this study. The letter A represents the specimen has the highest permeability, and letter D means the lowest permeability. We can see geosynthetic combined fiberglass and polyester with no asphalt retention rate. Basically, they are PMC1 and PMC2 provided the best moisture barrier function. We also find PGM had much higher permeability than other geosynthetic products. One possible reason is these products might be damaged during the compaction of the top layer. Similar to the permeability test, the laboratory samples for bond strength test were also drilled from the compacted slabs. We compacted 2-inch thick, dense graded asphalt slab for the bottom, and then shooting the tack coat, placing geosynthetic, pouring dense graded loose mix, and then compacted top 2-inch asphalt slab. After that, we drilled the 6-inch diameter course and then run the uncut bond strength test. These last two figures at the bottom shows the uncut bond strength test device and the schematic loading plot. Basically, we want to evaluate the interlayer bonding properties. Here are the bond strength test results. A proper bond between pavement layers is critical to provide satisfactory long-term performance for pavement structure. NCAP recommended the minimum bond strength is 100 psi. This can ensure adequate interlayer bonding for asphalt pavement. As shown in this table, according to the use of geosynthetic products like PFR, PF, or PGM fully met the bond strength criteria, while the use of PMC1 marginally satisfies these criteria. But the use of PMH and PMC2 could not meet these criteria. In general, the specimens with fiberglass-based geosynthetics except PGM showed less bond strength than those with polyester or polypropylene-based geosynthetic interlayer. From a statistical point of view, we see PFR, PF, and PGM showed higher bond strength than others. In this study, we also investigated the recyclability of geosynthetic interlayer. We evaluated the performance of asphalt mixtures containing 30% wrap with and without milled paving fabric. Here we evaluated a new paving fabric developed by Propex, and this product was milled from a field project in California. We performed 3 performance tests, including tensile strength ratio test to assess moisture susceptibility, hammer wheel tracking test for rutting resistance and moisture susceptibility, and Illinois flexibility index test for cracking resistance. Here are the TSR test results. Through the TSR test, we found that asphalt mixtures containing milled paving fabric had much greater dry and wet tensile strength than the minimum values required by Caltrans specification. Overall, the TSR ratio was 0.93, indicating the asphalt mixture containing paving fabric had very low moisture susceptibility. For Humble tracking test, Caltrans required that at 15,000 Humble passes, the rut depth should be less than ½ inch. We can see the asphalt mixtures containing paving fabric had excellent rutting resistance. After about 20,000 Humble passes, the rut depth still around 3 millimeter, which is much lower than the Caltrans specification requirements. In addition, from these rutting curves, we did not see any inflection point, or we call stripping point. This indicates the material has no moisture damage issue. The last performance test is Illinois Flexibility Index test. This is a cracking test using the monotonic loading, and this test gonna finish till the specimen is completely broken. And we can see the left figure shows the idea how to calculate the flexibility index. Basically, we use the fracture energy under the curve and also using a load slope to calculate this parameter. Generally, a higher flexibility index means a better cracking resistance. As shown in the right figure, we compared asphalt mixture with and without paving fabric against the NCAT test track section N1 mix. NCAT test track section N1 showed slight top-down cracking distress after 10-minute ethos of trafficking. These 10-minute ethos of trafficking could equal to 10-year service for the heavy volume traffic road. As we can see, asphalt mixture containing paving fabric had better cracking resistance than N1 mixture, indicating very good field top-down cracking performance. And if we compare this asphalt mixture containing paving fabric against the control mixture, which did not include any milled paving fabric material, we can see these two mixtures have comparable flexibility index, indicating they have comparable cracking resistance. Here are the conclusions for this study. Geosynthetic combined fiberglass and polyester with low asphalt retention rate provided the best moisture barrier function than other geosynthetic interlayer products. Polypropylene or polypropylene with polyester material had higher bond strength than fiberglass-based geosynthetics in general. Asphalt mixtures containing this new mutable paving fabric had excellent resistances to moisture, rutting, and cracking damage. That's all my presentation. Thank you for your attention. If you have any questions, please let me know.
Hello, everyone. My name is Eli Coelho, and I work as an engineer for TRI Environmental, and I lead the Transportation Research, Testing, and Services Division. The co-author for this paper is David Andrews of Propex, and Propex was the sponsor of this effort. I'm going to talk to you about a project that we recently did to consider new ways to evaluate the performance of pavement interlayers used to mitigate reflective cracking using TRI's full-scale rolling wheel load tester. Geosynthetic pavement interlayers are polymer materials used to improve asphalt pavement overlays. There are a variety of products for this application, each which attempts to improve the pavement overlay through one or more mechanisms: prevention of water infiltration, pavement reinforcement, or crack mitigation. In terms of crack mitigation, some interlayer products provide reinforcement in the area around the crack through improved tensile properties. These products typically include a stiff grid-like structure within their cross-section. Alternative products are used to decouple the existing asphalt layer from the new overlay. These products are typically thicker, non-woven materials that provide stress relief by spreading the stresses over a larger area. Both types of crack mitigation products were used in this study. Related to crack mitigation, a variety of tests have been used to evaluate the performance of these types of products. Most are benchtop size, but more recently, large-scale tests have also been used. TRI owns and operates a large controlled laboratory facility to evaluate the performance of full-scale pavement simulations. Featured here is TRI's Accelerated Pavement Tester, or APT. The APT uses a dual-wheel assembly to load the pavement surface as it rolls along an 11-meter-long track. Our client was interested in whether this facility could be used to evaluate the performance of pavement interlayer products when used as crack mitigation. Test sections are built inside a building that features a concrete-lined pit that is 3.35 meters wide, 11 meters long, and 1.2 meters deep. Test sections are built using full-size construction equipment. Construction begins with the subgrade, topped with base course, and finally asphalt. The test sections that were used in this study were actually built and tested for a separate client. However, because the test track is wide, the outer edges of the pavement were still in good condition and could be used for this feasibility effort. The next several slides will show you how the test sections were constructed. These two photos show the grading and compaction of the subgrade. The subgrade was a local fill material typical of South Carolina. It was constructed at its natural water content. The final depth of the subgrade was 0.9 meters and had a CBR strength of approximately 5.4% based on dynamic cone penetrometer, or DCP tests. The base course was 38 millimeter minus well-graded gravel. Final thickness was around 275 millimeters. It was built in several lifts, and compaction was done using a vibratory roller. Asphalt construction was done by a local contractor using full-scale paving equipment. It was built of a single layer that was around 81 millimeters thick. The final surface of the test area prior to loading is shown here. The traffic from the original project followed the lines in the pavement in the center of the test sections. Traffic for the interlayer experiment was done on the left side of the pavement as shown in this picture. This experiment was designed to see how well each product suppressed reflective cracks in the pavement under traffic loads. Because the pavement was new, cracks were simulated by cutting through the entire depth of the pavement using a wet saw. Cut widths were approximately 5 millimeters wide. A plan view shows the 7 transverse cuts and single longitudinal cut. This created 5 cracks that were bounded on both sides by independent blocks. Application of the interlayer products was done in a manner consistent with their installation in the field. Emulsions were determined for each product and applied using a hand sprayer. Masking paper was used to control the boundary around each test section. The following table shows the properties of the 4 products used in this experiment. 2 polyester mats having an internal fiberglass mesh were used as reinforcement. These are products A and B in the listed above. The 2 non-woven products, products C and D, were used as bond breakers or stress distribution. The products were cut to fit as shown in the following diagram. As you can see, they overlap both the transverse and longitudinal cracks. A control was used as the do-nothing case. Here you can see how the interlayers were installed on the pavement surface. And this is what it looked like after installation. The entire pavement surface was overlaid with a single lift that was about 57 millimeters thick. A white stripe was painted on the road surface directly above the transverse crack to help make the reflective crack more evident. A time-lapse camera was set up on each crack to take photos every 15 minutes. Knowing the traffic level as a function of time was to help link traffic level to the appearance of the reflective crack. The idea was that the test sections with cracks appearing at lower traffic levels performed worse than test sections where the crack takes longer to appear. Using this supposed data, benefit could be calculated as the ratio of traffic passes of the reinforced test sections as compared to the unreinforced or control test section. Trafficking was done with the APT set to apply 40 kilonewtons of load across the test sections. Traffic was applied bidirectionally, 24 hours a day. No reflective cracks were noticed during the first 80,000 traffic passes, so it was decided to cut the overlay along the longitudinal crack to decouple the test blocks in a way that would concentrate stresses on the transverse crack. Trafficking was resumed until 195,000 traffic passes were applied. Trafficking took approximately 2 weeks, and during this time, no reflective cracking was evident in any of the test sections based on visual inspections of the pavement surface. A wet saw was used to remove the blocks from each of the test sections and investigate what happened. In this case, the edge of the pavement was cut to reveal the side of each transverse crack. One thing that was apparent in all 5 test sections was that the saw cuts had healed during the trafficking. This healing effect may be chiefly responsible for the lack of reflective cracking. The saw cut crack in the control section also healed, but it did show a small reflective crack that had begun. Here you can see a side view of the crack in the control test section. Despite the lack of quantifiable performance data from this study, there were still a couple of valuable takeaways from the project. First, a filler should be used to keep the transverse cracks from healing together during trafficking. Sand is sometimes used for this purpose on smaller scale simulations. Second, the edge of the pavement should be exposed to more easily see crack progression as a function of traffic, as the visibility of surface cracks is difficult to see, and progression of crack growth would be more informative. Thanks for listening. I hope you found this informative. Please reach out to me if you have any questions or would like to set up a test of your own in our lab. Good day.
Hello all, thanks for tuning into my presentation. I'm Dr. Vinay Kumar, a postdoctoral fellow at UT Austin. In this presentation, I'm going to discuss about the asphalt strain response and the settlement response that we have captured from the field sections that consists of geosynthetic reinforcements under static plate loads. We all know that flexible pavements over their design life develop various types of distresses like fatigue cracking and rutting due to a number of factors which include inclement weather and traffic conditions. So basically these distresses reduce the serviceability index and require an immediate rehabilitation. So the pavement agencies typically install an asphalt overlay on the existing road surface to restore the serviceability. However, if these existing distresses are not treated well before overlaying, then the overlays may develop reflection cracks, and which may eventually result in premature failures of the pavement system. Reflection cracks are the major mode of failures in asphalt overlays, and there are a number of treatment techniques to retard the rate of reflection cracks. Among them, the use of geosynthetic interlayers is very promising. This is because of the various functions that the geosynthetic interlayers provide to resist the reflection cracks and in turn enhance the performance of the overlay and the entire pavement system in itself very significantly. So as said earlier, geosynthetics provide a number of functions when placed at different levels within the pavement system. Specifically in this case, when the geosynthetics are placed at the interface of the old and new asphalt layers. And again, depending on the type of the geosynthetics adopted, they typically provide waterproofing or moisture barrier effects, stress relief, reinforcing effects, and confining or stiffening effects within the pavement system, which typically enhance the performance of the pavement system invariably. Researchers worldwide have adopted various test methodologies to understand the influence of geosynthetics and the various mechanisms involved in retarding reflection cracks and enhancing the overlay performance. So basically, a few of the main evaluation methods include beam fatigue tests, bond strength tests, and pavement model tests. However, these tests do not entirely replicate the real field conditions. In addition, the field evaluation trials involving geosynthetic reinforced overlays are also very limited in number. With this background on geosynthetic functions and their evaluation methods, the objective of this study is to basically assess the strain and the settlement response in a geosynthetic reinforced and an unreinforced highway sections under a static plate load test. As part of a rehabilitation plan along a highway section in Texas, a 3-inch thick asphalt overlay was constructed over the existing pavement. So we basically took the opportunity to use the stretch of highway section to investigate the effectiveness of adopting geosynthetics in asphalt layers. So specifically, we considered an unreinforced and a geosynthetic reinforced section for this study, as shown in the figure. And the existing road profile consisted of an old HMA base and sub-base layers of more or less similar characteristics in both of these sections. The 3-inch thick overlay, however, consisted of a 2-inch thick type D layer overlain by a 1-inch thick TOM layer. The geocomposite interlayer adopted in this study was basically a fiberglass grid with a fabric backing, which had an ultimate tensile strength of 100 kilonewton per meter at 3% strain in both machine and cross machine directions. It is also important to note that an asphalt strain gauge was installed at a depth of 3 inches in the old pavement before the installation of geosynthetic and the overlay. So now moving on to the experimental program, the static plate load test device adopted in this study is in accordance with the European standards. It basically consists of two main components, the loading system and the settlement measuring system, which can be seen in the picture here. And the loading system typically consists of a 300 millimeter diameter load plate and a 50 kilonewton capacity load cell, a hydraulic jack, a hydraulic pump, and a high pressure hose. Whereas the settlement measurement system consists of a rigid rotating arm, a support frame, and a displacement transducer, which basically helps us to measure the plate settlements. The plate load test was performed in two phases, which is before the installation of the overlay and after the installation of the overlay. And as you can see from the figure, the typical test procedure included 3 loading stages and 2 unloading stages with a waiting period of 120 seconds after each stage, basically for the settlements to stabilize. The settlements and the strains corresponding to these loading and unloading stages were also measured. And in the next few slides, let's take a look at these settlement and strain response in both reinforced and unreinforced section and see what we can learn from them. Typically, the response under a plate load test is presented in the form of a load settlement curve, However, in addition to that, the time corresponding to each of the loading or unloading stages was carefully recorded in the study, which can be basically used to correlate the settlement and the strain response corresponding to any of the loading or the unloading stages as presented in the figures. From these figures, we can also see that both settlements and strains increased with an increase in the load and vice versa. However, an important observation to make is the time corresponding to a settlement which is consistent with that of a strain, which basically suggests a good correlation between the settlement and the strain data that has been recorded. This is basically the case for an unreinforced section, and let's see what's the scenario with a geosynthetic reinforced section. All right, so from these figures, we can see that the settlement and the strain responses for a geosynthetic reinforced section is quite similar to that of a controlled section. Now, for simplicity's sake, in these figures, we've considered the settlement and strain responses only for the loading stages. Also, we can see that even though strains in control section is higher than that of a reinforced section, the settlements in control section is consistently lower than that of a geosynthetic reinforced section. This probably may be due to the influence of ambient and surface temperature during the tests. We also know that asphalt mixtures are viscoelastic under small strain conditions, which is a function of time and temperature, which basically means that the temperature significantly influences the resilient modulus of the asphalt, which in turn influences the settlement and strain values. Initially, to understand the influence of temperature on the modulus of asphalt layer, we performed dynamic modulus test on core sample at different temperature and load frequencies. And we eventually developed a dynamic modulus master curve for the mix, as shown in the figure, which can basically predict the modulus for different temperature and frequency ranges. Further, making use of this master curve and the complex modulus equation, we determined the modulus values for test sections corresponding to the temperature at which the PLTs were performed, and also at a standard reference temperature of 77 degrees Fahrenheit. Further, we performed a multi-layer linear elastic analysis for the pavement test sections and repeated for different asphalt modulus values, and the corresponding surface settlement and tensile strain at a depth of 6 inches were determined and plotted as shown in the figures. Models were then developed to estimate the settlements and strain values for the modulus values that were determined previously. Settlements and strains in control and geosynthetic sections were basically normalized with that of a reference temperature to obtain the temperature correction factors, which were then eventually multiplied to the settlement and strain values recorded. After applying the temperature correction factors to the raw data presented in slide 12, we basically obtained the temperature corrected settlement and strain values as shown in these figures. From these figures, we can also see that the settlements in control section is still lower compared to the geosynthetic reinforced section. This is probably due to the pre-existing conditions of the pavement section, which will be discussed next. Here we can basically see the load settlement plots for both the test sections prior to the installation of geosynthetic and overlay. It can be observed that the settlements in control section were always lower than that of the geosynthetic section, even before the installation of geosynthetic and overlay. So, to better understand the influence of pre-existing conditions, the settlements measured on old HMA and on overlay in both the test sections has to be compared. So after comparing the settlement data, we came up with these reduction in settlement and reduction in strain plots. We can see that settlements on the overlay increased by 140% in control section compared to the old HMA, while settlements on overlay reduced by 6.5% in geosynthetic section compared to that of old HMA. In addition, a reduction in tensile strain by 90% was witnessed in geosynthetic section, irrespective of the pre-existing pavement conditions. All right, so we can make the following conclusions from this study. The surface temperature and pre-existing conditions significantly influence both the plate settlements and asphalt strains recorded under static plate loads. The plate settlements on the overlay was found to be 140% higher than that on the old pavement in control section, owing to the stiffness of oxidized old asphalt layer. The geosynthetic sections effectively resisted the settlements under plate loads due to the additional flexural stiffness and resilience provided by geosynthetics to the asphalt layers. A 90% reduction in tensile strain was observed in geosynthetic section compared to that of control section, irrespective of pre-existing pavement conditions. Overall, it can be summarized that geosynthetic reinforcement was effective in resisting plate settlements and minimizing the critical tensile strains responsible for asphalt cracking. Questions are welcome, and thank you for your interest.
Welcome to Geosynthetics 2021. I'm Jeb Tingle with the U.S. Army Engineer Research and Development Center. The title of our paper and presentation is The Large-Scale Laboratory Box Testing as a Performance Test for Geogrid Base Reinforcement in Pavement Applications. I'd like to acknowledge my co-authors, Dr. Jeremy Robinson, also with the U.S. Army Engineer Research and Development Center, Eli Coelho with TRI in Environmental, and Dr. Errol Tutumler with the University of Illinois at Urbana-Champaign. In the pavements community, there is a lack of a widely accepted link between geogrid properties and performance within pavement foundations. Due to this lack of widespread agreement, the use of geogrids for base reinforcement has been limited. The lack of performance quantification has retarded the development of universally accepted material specifications. And these lacks of specifications has created uncertainty in practitioners regarding the performance benefits compared to the costs of the geogrid products. The objective of this presentation and the paper is to present large-scale laboratory box testing as a performance test for evaluating the benefits of including commercial geogrid products in pavement foundations. Establishing a reliable performance test will allow the geosynthetics community to develop performance-based specifications that should help practitioners routinely implement geogrid products for base reinforcement applications. So the question is, why large-scale laboratory box testing? Well, we need a way to evaluate the behavior of pavement materials in a laboratory environment. Smaller-scale laboratory apparatus cannot reasonably capture the behavior of geogrid-reinforced base course materials. Due to small sample size, boundary conditions, and scaling effects, small-scale laboratory tests are not appropriate for understanding the global behavior of geogrid-reinforced base materials. Alternatively, full-scale testing could be considered. However, full-scale testing is very expensive, and the cost of testing numerous products in a short time frame is cost prohibitive. Thus, large-scale laboratory box testing offers a satisfactory alternative to these test methods. Table 1 shows examples of large-scale laboratory box testing conducted since 1987. The table summarizes historical test setups, equipment, and applied loads for different experiments that have been used to evaluate geosynthetic reinforcement within pavement systems. The dimensions of the boxes have varied, but are sufficiently large to capture the global behavior of the geosynthetic reinforced pavement sections. Steel or concrete boxes have been used to minimize the deflections in the boundary walls to ensure that consistent load response behavior of the test specimens is achieved. Looking at the table, you can see that many of the tests simulate an equivalent single axle load, or easel, to represent highway loadings of pavement systems. In addition, looking at the load frequency, you can see quite a bit of variability early in the test program from 1987. However, since 1999, many of the researchers have used a frequency related to 0.77 hertz. Thus, much of the dimensions of the boxes and the load mechanisms have been similar. This slide shows Table 2 from the paper. Table 2 reports the material and pavement profiles used in large-scale laboratory box experiments. The table demonstrates that a wide variety of pavement materials have been used in the pavement box experiments. Different subgrade strengths ranging from low strength to high strength have been used in these simulations. Also, various geosynthetic materials have been used in these experiments, including geotextiles and geogrids. These geosynthetic materials have been placed at various locations within the pavement system, often at the interface between the subgrade and base course material, but in some instances at different layers within the base or subbase materials. In addition, the tests show that there have been different experiments with both surfaced and unsurfaced pavement sections. Thus, tests have been conducted on asphalt concrete surface sections as well as aggregate surface sections. This table demonstrates that large-scale laboratory box testing can be used effectively for all different types of pavement materials and thicknesses, and these results could be used for representative pavement sections. Now that we've reviewed the historical testing of large-scale laboratory experiments, why do we need to standardize large-scale box testing? First, we want to ensure that there are fair comparisons of competing geosynthetic products. Secondly, we want to utilize the best practices to ensure that tests and experiments are conducted using the best possible procedures. Third, we want to allow comparisons between tests of different laboratories. Fourth, this standardization would demonstrate the repeatability of test results between labs that would give practitioners confidence in large-scale laboratory box testing results to use as a performance characterization for geogrid materials. Utilizing the literature review of large-scale laboratory box tests, the authors have developed recommendations to standardize the testing procedures and equipment. First, the equipment recommendations include recommendations for both the box characteristics and the loading mechanisms. The large-scale laboratory box dimensions should be on the order of 1.8 meters by 1.8 meters in plan view and at least 1.3 meters deep. Minimizing the potential for wall deflection during loading is a key concern in the selection of materials and design of the box. The box should include a removable wall for model pavement construction to allow access to the construction team to prepare the samples for experiments. The loading mechanisms should be consistent as well. First, the researchers recommend a simulation of an equivalent single axle load, which equates to a 40 kilonewton load on a 305 millimeter diameter steel plate. At the bottom of the plate, we recommend that you include a 6 to 12.5 millimeter thick neoprene rubber pad for improved stress distribution along the edges of the steel plate. We also recommend the use of hydraulic loading versus pneumatic loading to provide a consistent load control mechanism. Although different loading frequencies and patterns have been used, we recommend the use of a sinusoidal loading system. The load frequency of 0.4 second loading and 0.9 second rest period equates to a load frequency of approximately 0.77 hertz, which is consistent with the results shown in the literature review. Seeding load of 0.5 kilonewtons should be applied to the plate at all times to ensure that the plate remains in contact with the surface of the model pavement section. This slide shows the equipment test setup for our laboratory at the U.S. Army Engineer Research and Development Center, as well as what a typical sinusoidal wave looks like with a frequency of 0.77 hertz. Based upon the author's experience, instrumentation recommendations are provided. First, an inline actuator load cell is required with an accuracy of approximately plus or minus 0.05 kilonewtons. Secondly, internal linear variable differential transducer, or LVDT, should be included to monitor the plate deformation. In addition, an externally mounted LVDT near the edge of the plate is recommended to monitor plate bending as well as to validate the internal LVDT data. In addition, a minimum of 3 LVDTs to measure surface deflection at different offsets from the center of the plate are recommended. To measure stress, earth pressure cells are recommended to be included at different layers within the pavement system. Furthermore, at least one pore pressure transducer is recommended to monitor the accumulation of pore pressures to understand the behavior of the pavement system under loading. One temperature transducer and one moisture transducer are recommended to monitor the environmental conditions to make sure that the pavement sections are consistent and that the quality of the pavement has not changed during the test cycling of the pavement section. To ensure that model pavement sections are constructed repeatably, construction recommendations are provided. Each model pavement section should be constructed as similar to field construction procedures as reasonably possible. Each pavement section should be constructed and tested independently to ensure that each pavement section performs as intended. Line the box with plastic membrane to retard moisture loss. Materials should be processed to the target moisture content necessary to produce the desired material strength for the experiment. In general, the geosynthetics are not anchored, although some experiments have anchored the geosynthetics or folded them up the sides. This is inconsistent with best practices. The compacted aggregate base should be left uncovered for exactly 48 hours after compaction. It is extremely important that each model pavement section be treated exactly the same and that the test cycling not begin until the exact curing period has been exceeded. Finally, if hot mix asphalt is to be used, we recommend placing and compacting hot mix asphalt slabs using conventional construction equipment at a secondary location, and then cutting those slabs into the desired dimensions and placing those in the box using a forklift to ensure that the hot mix asphalt is similar to what you would expect in a highway or airfield pavement. This slide shows some pictures of the large-scale laboratory box, the construction of the subgrade, installation of instrumentation, placement of the geosynthetics, compaction of the aggregate base, compaction of the hot mix asphalt, and the placement of the slab. In summary, large-scale box testing has been historically used to capture the global performance of geogrid reinforced base courses. Standardization of large-scale box testing can feasibly provide a repeatable means of the evaluation of product performance. Standardization of large-scale box testing can also lead to performance-based specifications for geogrid base reinforcement applications. These Performance-based specifications can lead to an increased utilization of GeoGrid technology by practitioners. For questions or comments or recommendations, this is a list of the authors and their contact information. We would welcome to further discussion on the topic of the standardization of large-scale laboratory box testing as a performance test for GeoGrid reinforcement of base course materials. Thank you for your time and enjoy the conference.